Okay, all these cycles, that's not so interesting. You've seen the V cycle and the W cycle. Yes, this is the so-called V cycle, this is a W cycle, and there's a whole zoo of such cycles, and again, it doesn't make much of a difference. It may depend on the problem. It certainly depends on the preferences or on the people that the person who codes this up is hanging out with, whether they prefer this or that or get something else. This here can be coded recursively. You basically just go to the next pulsar grid until you have to stop. And well, from this grid, you go to the next pulsar grid, do something there, and then you go back. And that do something there is just the same procedure. So that's recursive. This here can also easily be formulated recursively. I forgot the recipe, and there's other stuff. One would want to do that recursively because anything else would not make much sense, because if you increase the grid size, you won't have to take special decisions. So V cycle, W cycle, and there's many more cycles. Okay, and now that's it about the method. Now let me tell you briefly what I plan to do with that in the first place. Actually, I didn't plan to solve this equation, or the one that you, for the H and G that you saw before. I plan to solve a slightly different equation that's even more nasty. The physical setting here is summarized by the keyword inertial MHD. That's basically what you get if you assume that you have a plasma consisting of electrons and ions that can move relative to each other. So you have a relative drift velocity, but that is quasi-neutral. So the charge density is still zero, as we are used to assume in classical MHD. But now the electrons can move relative to the ions, and under certain settings, the inertia of the electrons becomes important. And this is, for example, the case in the ionosphere. If you have a dilute plasma and you have alpha waves there, well, we all know more or less how alpha waves look like. So you have that magnetic field, and you have some restoring force if you bend the field lines, and that's all very nice. Except that it's not. It's a nice way of interpreting stuff, but it's not really what happens. What happens is you have that conducting fluid, you have the magnetic field, the fluid moves, a current, an electric field gets induced, correspondingly current flows, and that current then interacts with the magnetic field, and the Lorentz force then is a restoring force, and so on. When I do MHD, I try not to think of currents. Some people they enjoy discussing currents, and that just makes things messy. If you can do with just the magnetic field and just have these nice field lines, which are rubber bands, as we all know, that repel each other, then you're done. That's the way of doing MHD if you can. Try to avoid currents. Now, alpha waves, actually, in reality we don't have that conducting fluid. In reality, we have electrons and we have ions. And then alpha waves look like, probably it's longer, look like this, or the current system associated with an alpha wave. Even if we write down the whole dispersion equation for the alpha waves and everything based on just the magnetic field, we can easily figure out the current. Now, obviously there are currents, right? The current system looks like this. It has to be closed, and that's still the case in that type of model because of quasi-neutrality. And wait a second, makes sense. This current here is carried by electrons, and that current here, at least in many cases, well, as I said, for example, in the ionosphere, is carried by the ion polarization drift. And I won't explain to you what the ion polarization drift is because I keep forgetting. But it's really a kinetic property. It's a plasma thing. The fact is it's based on the fact that ions gyrate around field lines and then they drift in one direction if there's an electric field, basically. So there is no such thing as just that anonymous current that is flowing and everything is fine, as things might probably be in an electron-positron plasma where the two charge carriers just flow in opposite directions. Maybe not even there. But there is a completely different role played by the ion current and by the electron current. And that's important for the ionosphere, for example, and the inertia of the electrons when they are accelerated here by the electric field is important in order to really correctly describe these alpha moons. And that was the physical setting that I was wanted to tackle. I won't do much on that because now I have other plans. So how do the equations, well, MHD equations, in big quotation marks, look like in that case? We have this equation, which is still the familiar mass conservation equation, although we now need to think about how to define rho and u such that we can write that in this form. What is about velocity here? We have an equation of motion that looks similar to what we had before, just that now we have the electron pressure here explicitly, and the assumption is, one assumption that enters here is that the ion pressure is small compared to the electron pressure, but that's still the classical pressure term, essentially. But then we have this additional term here that enters with a mass ratio of electrons and ions. So you might think you can just forget about this, but actually this term can be considerably larger than that because the electrons are also faster, and VE is essentially the velocity of the electron. Well, it's a relative velocity of the electrons in electron velocity minus ion velocity. So we can't get rid of that, which took me some time to find out. And then for the induction equation, we have something quite similar to what we're using now, and it's very convenient to write it in terms of the vector potential. Here, you would regret not doing that. In classical MHD, many people probably are irritated that we use the vector potential because it's somehow more natural to use the magnetic field directly. So we have the A by dt, we have the induction term, we have the ohmic diffusion term, then we have possibly some additional electric field components like the Hall electric field and the electron pressure electric field, depending on the parameters, they might be important or not. But then we have, the gauge potential. So this is an arbitrary scalar here, this quantitative side. That's all the stuff we know. But then we have here the so-called electron inertial length, and I should have written down somewhere what that exactly is. But basically that, let's see, that becomes important if the plasma is dilute. And then we have this nice divergence of this tensor product, well, dyadic product of uj and ju. J is the current density, u is the velocity. And then we have, again, this effective derivative here with the electron drift velocity, the relative velocity of the electrons compared to the ions. And, well, all of this is not too bad. I can show you how the Hall term looks like. That's just J cross B, which looks very innocent. It's not that innocent because numerically you can run into trouble. But as I said, under some circumstances one can even neglect that, even though the other terms are important. Electron pressure is not a big deal, but it now contributes to the electric field. But well, this here is slightly worse because that's the derivative of the current, and that means that's the third derivative of the vector potential, which we would have to calculate in order to get that. But we can do that if we really have to. If inertial MHD pushes us to do that, we can do that. And then here, this is just a standard kinetic derivative, also not with the bulk velocity, but with some other velocity, but we also know how to do that. But the structural change, the fundamental structural change here is this term. Here we have 1 plus electron inertial range squared, curl applied to the time increment of the vector potential. And it is tempting to somehow try to get that gauge potential in here in order to allow you to write a Laplacian instead of curl, because if we have to invert the Laplacian, that's fine, we can do it component-wise, even if it's a vector Laplacian here, and we could just hook into the classical multigrid stuff, but we can't. It turns out that it has to be there, and as soon as lambda E is not constant, as soon as lambda E is a function of position, and that's the whole interesting stuff here basically, we can't turn that into Laplacian. So we have to do something about that curl operator. Well, basically we have to evaluate the right-hand side, just as we do now with a few extra terms. And then, before we call that dA by dt, we have to take that and apply the inverted elliptic operator here to that. And then we have the dA by dt, and then we just do the normal time stepping. It's just that one inversion of that elliptic operator that we have to apply in between.
What is rho? Yes, rho. Then it's n.
Rho. N here is the particle density of the electrons, which is the same as the particle density of the ions, except for the charge number, because we have quasi-neutrality. So think of N as the electron particle density. Then if you take into account that the electron mass is small, rho is, the density is really just given by the ion mass.
Yeah, then is a former slide. We can do this assumption on the momentum equation. No, before. Here, when you see the VE, yes, here.
No, as I said before, VE is MEVE can often be comparable to MIU or to MIUI. And but even though the electron mass is small, the momentum transported by the electrons in this direction is comparable to, can easily be comparable to the momentum carried by the ions in that direction, because that velocity is much larger than this one, because that length scale is much larger than this one. So initially I just dropped that term, but then I did the complete derivation and didn't drop anything, and only in the end I figured out which terms I can really honestly drop without making additional assumptions, and that's what you get. To get these equations, one can just write down a two-fluid model, equations for the electron fluid and the ion fluid. You assume a friction term, just like very similar to what blood does. A friction term is proportional to the velocity difference and all that stuff. And in the end, after quite some algebra in order to get this sort of stuff, you end up with that. Yeah.
Yeah. Why then can't you add the curve to the right hand?
Because we have the time derivative here.
So what?
What?
Yeah, like it's okay, like it's an like it's electric field then, right?
Sure, but still, formally for the equations, for the variables we're using, it's a time derivative. What we are solving in the code right now, and I really don't want to change that without any good need, is df by dt is some operator that is just a spatial operator acting on f. It's a nonlinear operator and everything, but there should, without really changing the structure of what we're doing completely, there should be no time derivative here. When you write these equations, you really get a dj by dt on that side very, very quickly and very easily. But then you have to work on getting that on the left-hand side and expressing it in terms of a, and that's exactly where this curl comes from.
But what we are doing, we're calculating the right-hand side and multiplying by dt. So could we not first calculate the right-hand side, using this term, and then take the curl of the right-hand side, and add this to the first right-hand side, and then multiplying by dt.
Can you?
What is it too inaccurate? So what we are doing is dA is something like right hand side times dt. So and we what we should perhaps do is right hand side plus curl right hand side, and this takes time t. But this is not something like this explicit implicit stuff.
You're applying the curl to the right hand side instead of the left hand side? I mean, how
First calculate this one. It should be something like this one, dA dt.
And then you calculate the correction.
Correction term, something like this.
Well, but I think then you just don't know what you're solving, because lambda e can be small in parts of the box and can be large in other parts of the box. So in some points you essentially can linearize that. Can you treat that as a linearized correction? And then I think that's what your scheme would boil down to. But at other points you basically just have Laplacian, well, depending on the gauge here, Laplacian applied to the a by dt. And then what you are doing is using the Laplacian instead of the inverse Laplacian in some sense, I think. So then I think this would go completely wrong.
Well, the core even it's easier than like you could do that. Curve of then it's just curve of the cross A, right, which is dt here, which is then curve of A, right? Which is then right dB.
That's how the whole thing started. That's where the equations come from.
Okay.
But the inertial effects add a time derivative to the electric field. So now again we have a time derivative on the right hand side. And if we bring that to the left hand side, then we end up exactly with what we have. So that's exactly where this all comes from. But unfortunately, it doesn't really fit well into the framework of what we have been doing so far. So I think we really have to invert that operator. Once we can do that, it's really just that one extra step. We evaluate the right hand side, and then we apply the inverted Laplacian to that, and then we just do the normal program. Okay. Bulk quantities, well, Mi is essentially, well, if you think of hydrogen, Mi is just the ion mass, which is hydrogen is the easiest way to think of this, but it could be anything else, and then if you just put the tilde in the right places, well, basically everywhere, then things are correct again. Density is just given by the ions, because the electron mass is so small. The momentum density, on the other hand, is given by the ions and the electrons, and these contributions are often comparable, as I said. if you do it like this, then you get that's the way to get the normal continuity equation. So if you define U like that, then you recover this equation, which is nice. And as you can easily see, U is then given by this combination of ion velocity and electron velocity. And you also, with that, you also get the conventional connected derivative here. That those two, this equation and that part of the vector term, they somehow go together. So that's the only way to reasonably define U. If we really want to have that U that represents as much as possible the whole fluid, and then we have that electron velocity because electrons drift relative to that. The way Vlad wrote similar equations is with a different approach. You can also just say you have the two fluids and each fluid does its own evacuation and mass conservation and so on, and that's equivalent. It's just that in this case, because mass is dominated by the ions, it is more natural to do it like this. And then we have the electron velocity, well, the relative electron velocity. That's the difference between electron and ion velocity. But this one is typically much larger than that, so essentially it is just the velocity of the electrons. And that's directly proportional to the current. So wherever we have a VE in these equations, we are, again, in these equations like here and here, we are again talking about the current. So this is a derivative of the current, this is a derivative of the current. They are tedious but straightforward to calculate. And then the magnetic, some relations involving the magnetic field. Well, this one you basically already saw. The current is essentially carried by the electrons, or at least if you know how the electrons move, you can calculate the current. This one you know, this one you know, this one still holds. And then you have this weird divergence of uj plus ju, and if you figure that out, you find that this term and that term don't involve stuff we don't know. If we already know the shear tensor, for example, for the viscosity, so we can just pull that out and project that on the current density that we also already calculate. This one is again a derivative of the current density, and you can write that as a projection on this term as a projection onto U of this tensor here. So the basic message is we have these third order derivatives of the vector potential, but that's not too bad. And yeah, the rest is also interesting. So the operator we want to invert is this one here, 1 plus this space-dependent factor lambda e squared, curl times curl applied to curl squared. And well, for the curl squared, I write this delta tilde, where delta is reminiscent of the standard Laplace operator, but it's not really the Laplace operator. You can write out this delta tilde, and you find that you're missing the second derivative with respect to x here, with respect to y there, with respect to z there, and you have all these non-diagonal terms. The vector Laplace operator would just be Laplace here, Laplace there, Laplace there, and 0 everywhere else. So it's a similar structure, but in a sense, at least on the diagonal, it's actually even simpler than the vector Laplace. It's just that, unfortunately, the three directions don't decouple, so we have to deal with this as a vector operator. So we want to discretize that. So if given a right-hand side G, we want to be able to calculate F, which is what we get if we apply the inverse of that elliptic operator to that right-hand side G, right? So if you rewrite that equation, basically that means what we have to solve now as a forward problem is operator applied to F equals G. Okay. So we discretize that elliptic operator, and then, well, you can figure that out to second order. As I said, in a sense, it's easier than the Laplace operator because we only have the y and z derivatives for that diagonal term, but then we have the off-diagonal terms, and there's no point in going through this in detail. It looks bad, but it's not too bad. It's straightforward, and it's a structure with lots of symmetry, so if you get it right for the first component and you pay attention, you automatically have it right here as well. And just for comparison, this here is the one equation that we iterate. That's the one that was missing before. If we, this would be the wind up with that.
I'm sorry, I have my.
Good luck with that. So that's what we did for the Laplacian. Of course, it simplifies if you believe in my typos, and this really is delta x, delta x, delta x. But generally, you can have different grid spaces there. And that's basically it. And yeah, I think I'll just stop here because I don't have too much more to say. So the message is, I have coded for the simplest boundary conditions, namely those ones. The multi-grid solver for, well, I have the equation here for this equation, Laplacian minus a constant, minus a function of position times f equals right hand side. And I think it works. I haven't done timings yet, and there's a lot of analysis that one probably should do that I haven't had the time to do, and that I'm unlikely to find the time to do for the near future. It is, if somebody really wants to, needs the inverse curl squared operator, the formulas are there, and you basically just have to replace this part in the multi-grid solver by that stuff here, and that changes the structure somehow because that's mostly because that's a vector operator now, but it's exactly the same recipe. If things go wrong because of anisotropy, then it is sort of known what to do, but that's additional work that then needs to be done. And one thing I should not forget to mention is my multi-grid solver currently is not parallelized. Parallelization sounds like it's a big deal. Actually, it's not as bad as you might think. Because it turns out that on each grid, you only, if you do second order, like all the stuff I discussed here, on each grid, you only need the next neighboring point from the processes that are adjacent to the given processor. And you can even communicate all the stuff in advance for the whole sweep down, and I think the sweep up, back up again. So for one full V cycle, you communicate once, and then you do your V cycle, and only then you communicate the next time. And you communicate quite a limited number of points. Well, it's a layer of one, which is less than what we do for the higher order spatial primitives here, and then anything else again is only adding in a geometric series that hardly contributes to the whole thing. So I haven't even started coding anything in terms of parallelization, but the problem is known and has been solved, and it shouldn't be too difficult, and in particular it shouldn't be too inefficient because we don't have to communicate as much as one would naively think. I first thought we just at every substep of the suite have to communicate all the information we need, but we can provide that in advance and just communicate first and then do the full suite. So that should be doable. But of course, again, it's doable. And I'll stop here.
Thank you all. Are there any questions?
This will never work for a non-equidistant grid because the function which describes the grid spacing will change during iterations? Or so you go from some fancy function down to a linear grid spacing.
I mean, you can formulate the thing, but you'll have the convergence problem I was talking about. Because even the ratio, the aspect ratio of your grid cells is varying then. But you can formulate this, you can do the same discretization, you just get the x prime and stuff there.
Yeah, but you know only x prime for the very first part, then you make the first first step to a newer group, and then the x prime will change.
You'll have to figure out the x prime also for the coarser grids. But we use a function. We use a given function to map the equidistant enumeration grid to the physical non-equidistant grid. And you can use that same. You don't need that function, and you can apply that on the coarser grid and so on. So it shouldn't be difficult to get that. But we will run into the convergence problems, and in this case, I think the only hope is that line or plane realization would do the job, because now it's no longer a grid that's the same everywhere. We just need to compare, is delta x significantly larger than delta y or not, because it will be larger here, but it's probably smaller there. Probably line relaxation would work in that case, but one would need to think it through.
Any more questions?
If I want to get true incompressibility in the code, would I use your multi-grid method and adapt it to solve the Poisson equation in various coordinate systems?
I'm not sure about the various coordinate systems. I think if you use spherical coordinates, you get the same sort of complications as for the non-equidistant grid.
Yes.
So you certainly have different ratios of the grid cells and so on. So you'll get the same convergence problem, and maybe line relaxation or plane relaxation helps, or maybe not. In Cartesian geometry, one should be able to use that in order to do incompressible stuff. But that always looks easier than it really is, because you're lacking some information that you get through the backdoor. And I think some people here, definitely some people here have experience with incompressible codes. But basically, once you have the Poisson solver, you can do that.
Or do the kind of stuff Andreas has been doing, but only in periodic coordinate system. We have been solving the Poisson equation, right? But only in periodic domains. But now we can solve it in non-periodic domains also.
Yes, except that currently we have only one boundary condition. I should also mention that in that connection, even if we code periodic boundary conditions and assuming that the problem that you predict somehow disappears, this would still not mean that this would be a plug-in replacement for the kind of stuff that Anders coded with the Fourier transforms. Because if you, for a stratified disk, when you have two periodic directions but you have one non-periodic direction, you have boundary conditions. Well, the boundary, I think that's the boundary conditions you were talking about, where you assume that there's no mass outside the box that involve the horizontal wave number. So it's natural to formulate those in Fourier space, and this is all coded already, although apparently not that much tested or used so far. But that's very natural. That if you use the multigrid method, you don't have the horizontal wave number because you're not in horizontal Fourier space. So you would have to do it right, you would probably have to do additional Fourier transforms, and then that's probably no point in doing that.
Couldn't you actually use Fourier transforms in the horizontal direction and just multigrid in the vertical?
Then you don't need one more.
I'm sorry?
Yes, but
you don't need one more grid, because if you only have one direction, you have to try diagonal matrix, and then you can invert. Then
So that's the way to go then in stratified disks.
Yes, it is.
Okay.
You free in two directions,
Alright.
and you invert a tri-diagonal matrix in the vertical direction. That's also the textbook recommendation.
Okay, I see. But this splitting can perhaps also, I mean, I don't know, in spherical coordinates, you basically have two periodic directions as well, and maybe you can use a spectral thing in phi and theta, do multigrid in R, let's say.
But I think again you would in R you would have a two-diagonal matrix, or if you go to higher order pentadiagonal or heptadiagonal, but still something that you can deal with in a more straightforward way. So,
More questions? Then I have one. Could it possibly make sense to start a cycle at the most coarsest grid? Because I imagine if you actually do this in the simulation and you use the converged solution from the last time step as your starting point for the current time step, which you probably do, then the large scales will change slowest. So
should be a good initial.
yeah. So and then starting at the core scale, it's almost there. And if you then add the corrections to the smaller and smaller scales, that might be an advantage.
That's a very good point. Right now, well, actually, the recommended cycle is called the full multigrid cycle, and that actually does start from the. I think it's basically something like this here, the W cycle, but without that part. You start at the coarsest grid, and then you successively you always come back to the coarsest, but then you go higher, finer and finer and finer. Currently, I really do the V cycle, and the main reason was that I don't know how to get the all the coarse-grained versions of the right-hand side if I don't evaluate the right-hand side at the finest grid. Then I know how to coarse-grain that stuff.
Mm.
But you are completely right. I could take all of that stuff from the previous time step. Once we use time stepping, my tests so far were just do the initial assume a density block, do the initial condition as an initial condition, and figure out the gravity field. So I just hooked that into your self-gravity stuff. But if you do time stepping, yes, you have all this information with relative good accuracy for the very first upward sweep, and that would probably also speed up convergence dramatically.
I mean, I can actually see this being extremely efficient. I mean, in the simulation itself, once, at least as far as run.x is concerned.
Good point. Yeah.
The treatment of ghost zones change at all as you move along the grid? I mean, you keep the same ghost zones, or you're actually multi-gridding those two?
I realize that I haven't thought this completely through. The coarser grids would have their own ghost points, which are way further out than the real ghost points that we're dealing with now. But again, if we use a symmetry condition to populate the 3 ghost cells for the hydro part, then we can use that to populate that one ghost point that we need if we do second order here, be it the point here, be it a point on the coarser grid there, or even out there. So I think it's the same philosophy that gives us a unique answer.
Did you discuss pluralization yet?
I mentioned that.
No.
I've only read about that, but that's very convincing. You can apparently just communicate the ghost cell values before you do one full cycle. And you can then use that for the whole cycle. So once per cycle, you have to communicate at all levels. And that should be quite good in terms of latency compared to the more naive approach. But I haven't coded any of that yet. What I have coded seems to work for the serial case, but that's it.
Okay, so let's thank Wolfgang